Recording in progress.
Okay, welcome everybody. So welcome for the last colloquium for this semester. And this colloquium will be given by our own faculty, Dr. Ananda Hota. Dr. Hota is a well-known astronomer and pioneer in the field, a pioneer in the citizen science research in Indian astronomy. He's been serving CBS for last 10 years, and that's why he doesn't need actually a formal introduction here. He has worked at various institutes such as NCRA TIFR, ASIA in Taiwan, Ayuka Pune, and ISER Behrampur. He did his PhD from IISc in 2007 under joint astronomy program, working at NCRA. And 4 of his astronomy discoveries have been press released internationally, creating large public interest in astronomy and bringing pride to Indian astronomy. So, so with this introduction, let me invite Dr. Hota for the term.
Thank you, Musan, for this introduction. I start this way always, that my talks are very informal. So when I see so many young students, definitely you should discuss with me as many naive questions that you wish to. This is the second time I am talking about astronomy from this platform. First time when I spoke, that was long back when I joined CBS 2013, very early 2013. It was evening, around 8 o'clock, 9 o'clock, all was full. Similarly, today this is not full, but certainly very young people are there. Okay, that is what is more exciting. My cover pages are usually packed with various information. Because this goes into kind of social media again. I'm very active in social media. So my cover page should be telling almost everything that you want to get a message about my talk. What is that? That is as you have seen in the notice board, the object that I'm going to talk about is at the left hand top, where it has been named yellow team that you have seen in notice board. That I have put some photographs here I will describe it. Practically, you can read monster black hole. This doesn't mean anything. It simply means that massive, million to billion times mass of our own sun. So that's how it's called monster. And you can see my affiliation. I'm leading basically this citizen science collaboratory called radathom. Radathom means real astronomy discovery sitting at home anywhere in India, free of cost. So how is it slightly different? And that I will describe it. I will describe the astronomy part of that and the socio-scientific part of it. That means here is a photograph from CBS, the first room on this board. Professor Chitra used to teach, I used to teach. What these students are not from CBS only, these only CBS students. They are from different parts of India. They have been selected based on their social media or internet-based activities. Then they are given training for 7 days. This is not only once, every year it has happened in CBS. This is 2018, that is 2014 picture. Similar to this, various institutes have posted our citizen science research training programs. And this discovery is based on that kind of students' discovery. Professional astronomers have used their advanced knowledge and advanced observation, but it is based on their discoveries actually. That is why it is citizen science discovery. So I'm UDC faculty, I'm located here, all this slightly hidden because of Zoom, that's all right. UM-DAE and CEBS, this is a radathom's logo, this is Collaboratory. I'm a member of International Astronomical Union. That is the oldest professional astronomers organization in the world. There is 12-kilometer array. Another big radio telescope that various countries are trying to make that will be 10 times bigger than the currently best radio telescope. There is India Consortium for that. I'm Astronomical Society of India. Any student can also be a member of that. Student astronomy, if you are interested in astronomy. So things are like affiliation, acknowledgement, whatever you think. So the cover page is packed. Every institution is. So message is an astronomical discovery. It is from a social scientific experiment called citizen science. Many institutions are in the process involved in supporting this activity. This has been happening since last 10 years. Okay, let's go. This is your talk. Just a reminder to everybody that I am recording this talk and we will be uploading this to YouTube so that many students like you and many outside CPS will be getting to know. For example, my co-author, my senior students who are interested to be part of the future. Again, our CPS has given a press release. So briefly 2 sentences from that. It not only tells what kind of discovery it is, it also tells that the system supports this kind of activity because it is a new way of involving undergraduate students into the research process, direct public participation in research. That's why the director congratulates and appreciate this activity. Not only CBS, 2 dozen institutes are supporting this kind of activity. I'm not only taking pride because they're leading that, but also because it is a new way of doing at science. Earlier, people used to think first you have to do education, finish the education, then join research. No. The time has come, the research landscape has changed in such a way the data amount is too huge, it's exploding. So something called big data problem. And the citizens in large number are coming to help scientists solve the scientists' problem. And radathom is slightly different. It is trying to solve the students' problem as well. I will come to that aspect now. So, as Goswami introduced me, that I have come in the international news 4 times. This is the 4th one. First, it was in 2011, exotic black hole galaxy system discovered with UM-DAE telescope. Then this was in the NASA news, black hole galaxy system, some kind of co-evolution we discovered in 2012. This was 2013 when I was in CBS. Farthest star that was discovered here in the tail of this galaxy. This is the next time I'm here, we'll be learning this now. This is from our press release page covering this thing. You don't need to go. Various people that are involved up to this first 3 star They are all professional astronomers, PhD degree holder. But from here, they are all citizen scientists. That is how this is interesting. That not only the professionals, not only who are PhD, JR, research scholar, anybody can participate. Not again like JR. So these are the team, all are Indian. Although he and she, RSU Observatory USA, he was in Paris that time. Now they moved to Spain. All of these are all professionals. They are in India. They are Indian students, obviously. Primarily, we have used the main credit goes to GMR, Giant Meteorological Radio Telescope, our own pride, is 3 times bigger than the American Best Radio Telescope BLA. These are 45 meters. How much is 45 meters? Roughly from one electric pole to another electric. That is 50 meters. So huge dishes, 30 of them are spread over 25 kilometers. I will show you the Google Earth picture there as well. Not only GMRT, our own Indian pride, but also used many other telescopes. What are they? GMRT radio telescope, which works in 1400 to 150 megahertz radio band. This is a radio telescope in South Africa. Meerkat is called. Like our satellite pieces, it's offset parabola. Its field is here. Another telescope, very large in the USA, I was talking about. Most productive radio telescope. Both the radio telescope along with GMRT, and then the optical telescope, 2 meter size, called HDSS in USA. This is again Canada, France, Hawaii telescope. So astronomers have this interesting culture of using telescope data from anywhere in the world. They have this interesting because share the data free. Anybody can use it. So that is how we use GMRT. We use GMRT, our own telescope time. Nobody else can take the data up to certain time period. This is our own property, intellectual property. But these were all free data. For example, this is a necessary part of understanding astronomical processes because suppose you are an X-ray astronomer. If you take a photograph of your body, you will see only the bone. Now you are a spectroscopy person, like Doppler ultrasound you do. You do kinematics study, how the blood is flowing in and out. Get it? That way, this is imaging radio telescope, like GMRT. This is imaging optical telescope. They have 2 meter size, this is 4 meter size. So various sensitivity, various way of looking at the same phenomena, you need to understand as a complete process what is happening. Like ionic gas can be seen in line, hot gas can be seen in X-ray, cold gas can be seen in radio. There are various ways of looking at it. We will come to this aspect later.
Within the radio telescope, is everything different?
Yes, this was the GMRT telescope, the data we have used, that is 300 megahertz data, and the Meerkat telescope, the data you have used, that was 900 megahertz, and this is 1400 megahertz. So that's our priority to look at what kind of process is different. For example, low frequency, when I go to GMRT, I will see the old relativistic plasma. If I go to high frequency, I will slightly see the fresh relativistic plasma. In one quick way, I am explaining this. So, for example, here again, I have used this telescope data to understand the spectral line to determine the distance or the redshift information. But this has been used for deeper observation to see the old stars outside the galaxy. So every telescope gives a slightly different information. So once I have discovered something with one data, I will try to look for peripheral supplementary evidences what is happening there. Let's move. This is the other concept that I have already described. This is the representative GMRT telescope we have used, and we have used a system for nationwide inter-university student network. The process that has discovered this thing. So this is not an astronomical discovery. Action of the paper, the radathomeindia and discovery of an active galactic nucleus, spewing a large unipolar radio bubble onto its merging companion galaxy. Very long process. It describes everything whole. The process that a citizen science process is discovered, black hole is spewing some plasma, it is going towards companion galaxy. This process was important because that describes everything this was never seen before. That is how this title itself describes. Apart from this simulation, real observation, molecular paper, it has been given press release by these organizations, as well as various Nature India, Times, Indian Express, various media has reported it. Give them the emphasis, usually science talk do not give them emphasis. Whole media is reporting. Why should we report their name? Why should it is Times of India? Why should it be Indian Express? No. Citizen science is a different approach. Because these are the medium who are taking the science to the mass, to the public, to the student, to the citizens, and they will come back and give a positive feedback and enhance the process of citizen science discovery. I can give you a direct example. When I had my first citizen science camp here, the student that came had actually made a newspaper cutting of my 2011 discovery, put it in front of her study table. This is what in astronomical discovery I'm fascinated about. I want to go and study this. And when they got this Facebook message that I have created a Facebook group to start citizen science radathon, that student actually came along with her mother, because she was not allowed to go alone. So that is why I love this aspect. We were there, I tell them. The media is connecting the society. The outreach, that's why it's important. You never know whose student is getting inspired today and tomorrow he will become another scientist. Okay, this is the reach basically I am telling you. That 20-second video that we have created, I will show you next. That was used by various video makers. You might have heard this reel, shorts, everything is happening these days. They are science communicators. They don't want to call themselves media people. They want to call them science communicators. Okay, so they are taking this message of this discovery to 50,000 people in Facebook video, 73,000 in YouTube. This is the website. So these many people are doing it, and they may come to work with me. That's one aspect. The other aspect is they are listening to an Indian discovery. In many videos, my name doesn't appear. They are simply Indian astronomer has discovered this. So this aspect of spreading glory of Indian science to various countries. Go to my website, I can show you that Thailand, Indonesia, everywhere the message is there, the news is there. So they are spreading a different meaning. We are improving our country's image in some sense. It's a big words, but I'm speaking from a small level, but that's true. Okay, so this is the simulation. Not for other simulation. This is not a real picture. The yellow pink one is the real picture. This simulation I will show you now. At the very early message, I will show you that. So these are basically artist view. Me and Hemant Bagela, their galaxies are rotating. Two elliptical galaxies with a very old stars. They are rotating. During the interaction process, they are going around their center of mass. The plasma shoots out. It hits the galaxy and returns backward. So, what is actually happening that there are two galaxies coming close to each other. Because of gravity, they are going around the center of mass. And this kind of disturbs. The moment they get disturbed, the orbit of this gas and star that is going around, then they kind of lose their circular motion. In technical word, they are losing their angular momentum. When they lose their angular momentum, like the satellite force, they get pulled towards the central gravitational potential. That is how they start feeding the central star formation in cases, and they are feeding the black hole as well. The moment the black hole starts accreting material or gaining something, some amount of that energy gets released as a jet. That is what is happening. The yellow blobs that you see, they are stars, like our sun, several billion, 4.5 billion years. But the pink color thing that you see is not gas, is not star. This is electrons. And possibly positron or proton, we don't really know, even after several decades of this discoveries of this kind of sources. That here there is no atom, no molecule, no gas, no emission lines, so it's difficult to find out real distance or real velocity. But there are observations to indirectly tell. So the particles that are ejected from this process, they are relativistic, means they are moving close to speed of light, almost 10% speed of light. When they move, there is a magnetic field in that region also. Around the magnetic field line, these particles will be relativistic individually, but there will be gravity around the magnetic field. And the whole block moves. For some reason, it's getting reflected. Nobody has seen from a galaxy the plasma block get reflected. That is what is amazing about this discovery. Second thing that is puzzling, I don't know how true that is. In future, it will be proven that the jet is always bipolar. The black hole's outflow process is always bipolar. It goes one way, the backside goes front and back, doesn't matter. But the other side, even now, our sensitivity is 1,000 times from the lowest to the highest brightness that we have discovered, we have detected. The ratio is 1,000 times. Still, we don't see any jet on the other side. Why this is happening? It's still a puzzle. Okay. So, both of these three aspects, that is the interaction of the galaxy and the jet, one-sidedness of the jet, and the citizen science approach for this discovery. All these things are very interesting, and that is why it is gaining public attention.
Color is a simulated color, is that right?
Sorry?
The color is a simulated color.
Colors are just because the observational picture, direct picture, red, green, blue. The red and the blue, it is mixing and becoming pink. So artificially, I have given this pink color.
No, you would have observed in the radio frequency.
Yeah, that is invisible.
Yeah. So whether you have an optical observation also for the same thing.
Optical observation is real data, visible data, but is color coded as green. Here it is yellow. This is an artist picture. So the real picture.
Make on the spewing pass.
Sorry. I want to go back to my presentation. I can describe it again. This yellow color is also artificial. But galaxies look yellowish, that is true. So I have given a yellowish color. This is made up of two frequency units. One 300 megahertz and 900 megahertz. 300 megahertz is put in red, 900 megahertz is in blue.
They are from different observatories.
Different division. Red is GMRT, I mean Indian GMRT, and blue is South African Milket. So the combination has become pink. So in artist impersonation, I have given pink to kind of match one to one. Yes.
That bipolarization is happening at the same time, or maybe other side could absorb by some other galactic medium nearby.
Yeah, see, in almost all cases, it happens bipolar. Both the sides are seen. And because of Doppler tuning, I can come later on. Sometimes one side gets enhanced, but that is not that strong that 1,000 times difference we have. It doesn't happen though. So it is possible that there is something else happening in between these two galaxies. For maybe extra gas may be there, which is making this plasma disperse more, get randomized, and we see. And on the other side, the density may be so low that it is not just visible. It may be there. For example, when you are not flashing a light, anybody smoking, you don't see the smoke. So some kind of process may be there that is doing this crazy thing. We are not claiming that it is one-sided jet. We are claiming because it is theoretically people have postulated that, but it is not seen anywhere yet. Okay, so yes.
You know that it is not.
Because in tens of thousands of radio galaxies that we know, the optical galaxy, elliptical galaxy in the middle, and we see the jet, radio jet going out in that both directions. So it's a very odd case. So that is why we cannot claim this is actually one-sided. We have to be a bit more careful and find more evidences. So, changing gear now, we have come to the beautiful animation that plasma goes and returns back. Coming to reality. What is reality? And dream we are aiming at very deep physics. Maybe Higgs boson, maybe first image of black hole, whatever. But reality is we are in an educational institute. which is a small toy or educational microscope, or a small red optical telescope. But we are always connected by dream and aim and career to a big physics part or a big biology, whatever you know. So how do you connect this huge gap? We are a very kind of 50-50 research from education institute. We have very good resources, very good faculty, but there are plenty of colleges all over India, but they don't have any chance of seeing an astronomer, right? Seeing a physicist who publishes papers, say in PRL, right? They have not seen. So how do they get inspired and get connected to research? For example, the first time when I heard about particle physics talk in my second year of BSc, I still remember the weekend, the big hall. The last thing that my teacher, wrote was Higgs boson. The first astronomy talk from a professional astronomer that I heard, I recorded in a radio tape recorder, quasi radio. So information is equally important as inspiration to the students. So coming back, let's connect the students who are access to this kind of toy telescope, educational telescope only, to data from big telescopes so that can be connected to big research. That is what in the collaborative model citizen science. That wherever you are, whatever may be your educational level, you have a chance of getting involved with a big research team. You will be properly guided. No, discover that is not possible. You have to be disciplined in a collaboration. That is what is the radathom. That we are connecting students from thousands of students from different colleges, learn something about LACO, what data GMRT can give and what does it mean. We will have our first lesson for many of you that the brightest star in the sky that your naked eye can see, GMRT biggest radio telescope cannot see. Because physical process is different. It is seeing something else. It is not an optical telescope, it's radio telescope. Okay, so connecting to big telescope, I said, every student will get to know what the data from a big telescope, world-class research telescope shows you. This is one world-class research telescope. If anybody knows, AstroSat, India's multi-wavelength astronomy observatory. Time allocation committee for AstroSat, there is a kind of a committee which gives time to the astronomers. This is an important topic. I want to observe, give me time. If you write a proposal, very systematic proposal, Professor Antia is here, who will be checking whether this is justified or not. Okay, that is how the science goes. That somebody checks in, gets time from the AstroSat, and you get the data to publish it. And that makes discovery, goes to news, student get excited. Human civilization's knowledge progresses. This is another telescope I have been talking to, GMRT. This is 45, you can see a Tata Sumo here, if you know that Tata Sumo model. Huge structures. Bit of a perspective. Dream reality, I told you, this is another perspective. 1930, 1950, Raman, Bhava, Saha, this kind of names, excellence, individual excellences. Then the time came that we want to produce wheat, we want to produce milk. That kind of white revolution, green revolution came. Then technology denied real science in India. Atom bomb test or defense related thing, nobody will give you technology to do it on your own. Then again, IP generation. Today we are at this race. That we have to be global leader in publishing paper, doing science, because defense, science, everything is interconnected. So we have to be competing with the world always. So research publication is always a global competition, right? So we have to think of a model where education and research are combined, and that has to be in a scalable way so that we achieve this thing, faster, sustainable, inclusive growth. That is why I'm not creating a computer which can serve 1,000 people. I'm thinking of creating a network of people, let them use whatever model they think, social media or YouTube, Gmail, whatever. Let them contribute. No school has taught me Ramayana and Mahabharata. I've learned it at home. That's how let the knowledge be so free and interaction be so free. Media has become two-way now. Social media, not newspaper that Times of India's editor doesn't know which Ananda Hota reading the newspaper. But that was a different deal. So let's connect biggest telescopes with the students. I don't want to go detail. This is our a big optical telescope in India, Nanita, 3.6 meter. You can see here. The world optical telescope, they are meter size and when they were commissioned. So in optical astronomy, India is to a large extent lagging behind. But these two that I said, the optical X-ray telescope, astrosat and GMRT, we are large. So here is a plot of showing the collecting area size of the telescope of world's radio telescope. GMRT is here. That means if you have a largest optical telescope, a largest radio telescope, you can see the farthest thing, or you can see the sharpest picture. Astronauts from all over the world come and use GMRT. This is GMRT 1D. You can see Google Earth picture. This is the real picture. The location, this white scene that you see at the steel wire mesh, the dishes are so big that you can see it from the top, from the satellites. This is another one. I will give you an example. This is our Indian astrosat, UV-IT telescope, ultraviolet telescope. Another one from NASA is called Galaxy. Galaxy telescope's picture is this ultraviolet picture of a star, many stars there, and Indian telescope picture is here. See the difference. That means here the resolution is 5 per second around, here it is around 1 to 2 per second. So if you have this better telescope, you are actually going to see something that nobody else has seen that before. So that is what is the power of the telescope. The moment you understand to interpret astrosat data or GMRT data, you are empowered by the power of the telescope. Whatever you will see, you are going to be seeing the image that is the largest angular resolution or view of the star formation in an extreme environment in the nearest jellyfish galaxy. Nearest means you can have the best and real resolution, angular resolution, linear resolution. Okay, so slightly coming to my topic again. 2011 paper I was talking about, first time when I came in various news, that this is GMRT's image. Red is GMRT image, blue is American GLA image, and HDSS optical picture is here. So there is a galaxy here. I suppose this is zoomed into you. The galaxy is shooting one pair of plasma block. Millions of years back, it has shot another pair of plasma block. Like somebody smokes and leaves. This plasma block is dispersing. It has become faint and bigger and dispersed. This is doing so, but this is fresh and new. So, with various methods, you can find out how many years back this plasma block did not get heated or did not get enough energy supply. So, when this plasma block basically starts decaying, starts radiating, starts cooling, starts dispersing, you can find out. For example, the block number, this block and this block, age difference between them could be 100 million years. From year to year, the plasma can reach in few million years. So for example, this to this, there is a gap, several tens of million year gap. What was the black hole doing for tens of million years? It was not creating jet. What? You don't know. No clear answer. So the plasma that comes out of the black hole accretion process, it continues for millions of years, stops for millions of years, starts again. It was all happening in big elliptical galaxies. This was for the second time, clear case or the first case clear time, that is spiral galaxy is known to create such kind of plasma blobs. That's how it became a news making. Probably first news making discovery from GLA. So then actually I thought, this is so simple. Anybody can just overplot radio optical and find out whether this is related to the central one is elliptical or elongated. But this is a rare, right? Rare to find that kind of box. Thousands of objects nobody has seen. So I it's simple now. I want to find a rare object. I want to find a rare thing that are difficult to find. If I go alone and search in the, let me give an analogy. Suppose while playing football, I have lost my golden ring. If I go alone and search, it may be impossible for me. I cannot find the hidden in the grass. But if I'm a principal of a school, I have 100 students. Roll number 1 search here, roll number 2 search here, roll number 3 search here. I can distribute and train them to look for gold. No, look for something circular, something yellow, something shiny. They did not be knowing atomic weight, molecular weight. So the details of advanced physics or astrophysics may be hidden from you, but you can all be part of making that discovery. So I have to explain what to discover in simple language, in structure and color. And that is how you make discovery. Once you discover that gold ring in the playground, I am supposed to give you suitable reward. What I do, I give authors. Because that finding was not normal, it was a really important fact. So, father of Indian radio astronomy, Professor Govind Suru, he appreciated because that was a discovery from GMR. So he appreciated me this way. Govind Suru, during Corona period, he passed away. Govind Suru of NCRTFR, who is not part of the team, described the finding as an outstanding discovery that is very important for cluster formation work and highlights the importance of sensitive observation at the meter wavelength provided by GMR. What is a cluster here? Cluster here is the scope cluster. You may have heard in the news. When there is a group of galaxies, that group is so big that there are thousands of galaxies. A galaxy has 100 billion stars, like our Milky Way galaxy. So that is the time basically I started thinking how to make a new model of making more such discovery. Not necessarily I have to come into the picture in the news media, but people have to be educated and involved in making more discovery. So this is what the idea is. Our country has largest pool of science and technology manpower, largest pool of IT companies and engineers, largest number of mobile phones or computer connected to internet through English information. If we can use this kind of a system, man-machine combined, human resource network and the largest telescope network, then we can do wonderfully that kind of science. So that is the answer, citizen science. That is why I returned India in 2012 to start citizen science. Okay, so GMRT has looked at all part of this stuff. Everywhere you look at, GMRT can cover 90%. Very south part we cannot see because we are in the northern hemisphere. So it has looked at all part of this star. So any part of this star you look at, there is an image made by Indian telescope GMRT. So why not start training people how to spot rare objects? That is what I started. I was trying to make a website from CBS that didn't work out. So finally I said, no, it doesn't matter. I can go to Facebook. Facebook, I can post an image, comment there. People will post another image, comment there. The discussion goes on. Later on, Facebook evolved. People can also comment an image. So we improve. Then the screen share, Zoom, Google Meet, Skype, everything is evolving over the last 10 years. So we are also evolving there. Okay. That is how I started talking to various organizations. They started helping to create a man-machine network. Today that network has grown in Facebook to 4,800. Not everybody is active, but there is a hierarchy. How many of them have been trained for 1 week long? How many of them are playing PhD? So that's why the hierarchy. Whatever anybody discovers, that goes slowly and get filtered and advanced study goes on up to the person gets an authorship in a paper. So this is a summary of radathom. We can say that we have a website. This is a website, radathomeindia.org, a Facebook group like this, 4,800 members. Discovery camp at various institutes. The picture that you saw like SBS, ICTS, CBS, various institutes I have done. And whatever they discover, when they go back home after 7 days training, they do it from home during the weekend also. The return is given to them. That their discoveries from home goes to the GMRT observation. As I said, GMRT has looked at every part of the sky only for 5 minutes. Only for 5 minutes looked at the part of the sky. Then when we go to observe the GMRT after a small preliminary report of discovery, we will be looking at that part of the sky for 5 hours. That's how a mobile camera photography versus a DSLR photography. You can see how much detail we can see. That's why with GMRT we further investigate and go to copies. If it is so good, without observation also wanted copies. So in a flying pyramid model, astronomy discoveries are happening at home that helps the career development, life development of the people involved. Out of 200 people that I have trained in this kind of 7 days camp, posted in different institute, 60 of them are doing PhD or MS abroad. There are many in India also. So this is how help in their career growth. This is our CBS camp in 2014. We took the students to go. Seniors can see some of the one known face. Unfortunately, the student of ours, brilliant all-rounder, good study, good play, all kind of medals he used to get. He passed away. I took them to meet Professor Bobin Soro. The inspiration, as I said, inspiration plus information both are necessary. This is our 2018 camp with some funding. That time there was no funding. Student and me went with our own money. Then 2018 camp, 2014, 2013. This is 2017, I guess. So every year it has been happening in cities and in many other institutes. So many other institutes like ICTS will be hosting us for 7 days. Free food, free stay, everything free. Enjoy swimming pool. Students were loving it. They get certified. And one of these participants can. Where is Arvind? He is co-author of this grad 12 paper. Similarly, this CBS camp also. One of them also, two of them are actually co-author. Here Vinas is co-author and here Megha is co-author. So the training in different places, long back 2014, they got trained and they are stuck with the system. She is a journalist, she is an editorial assistant. She is not a scientist research coach. Okay, so let's move. Vigyan Samadhan called me. I went to different cities and gave talks involving public because bigger than GMRT, India is investing in thousands of crores probably to build SCAR. So public needs to know, public needs to be excited about what is this big thing that India is making. This was the hierarchy I was telling. We have got enough. We have two here. Okay. Okay. I will quickly tell what is the difference in Veblen and Hawk. Everybody thinks stars in this kind of constellation, right? The moment you think about astronomy, people think stars. But now this kind of constellation, I'm going to look at the stars, I'm going to look at the radio. We'll see what you see. So what we look at? We look at in multiple wavelengths. Ultraviolet, infrared, radio. So I'm going to look at some constellation called Kritika. Kritika in plates. When I look at that constellation, you can see optical light, UV light. Optical light, UV light from the stars. But this one that you see is bright in infrared. So the stars are some objects which are like black body, which are 6,000, 7,000 degrees hot. That's why they are brightest in optical band. But this block that you see, that is brightest in infrared because that object is actually cold. The cold means 200, 300 degree Kelvin. That is why the maximum emission comes in 22 miles. So the brightest stars are not visible with the radio telescope GMRT, whose emission is seen here in contours. Stars are undetected in radio telescope, but something else is seen. What is that something else? Something else is the background galaxies, where the black hole is active to accrete some gas and create this plasma clouds. Because these are thermal objects, they are bright in optical band. Thermal object, cold, bright in infrared band. These are non-thermal objects. They are because the black hole's accretion process. So completely different thing you will see when you go to different levels. For example, this one. This is a star. The star is in optical, but when I go to infrared, I see an earth-like thing. What is that? Interstellar medium. Whatever gas, cold gas is there, far away from one star and another star, that medium is very cold. For example, the backside of moon, you're not getting sunlight. Here it is getting 150 degree. This side will be minus 150 degree. It's very cold. What is the temperature of the black body? If it is 150 degree minus 150 degree, what is that wavelength that we are emitting maximally? Lambda max T constant with displacement law. That kind of object, cold object, will be bright in infrared. So hot object will be seen in X-ray. Warm object, optical. Very cold frozen object in infrared. Even cooler will be in short millimeter radio. But something become non-quantum, relativistic, that can go in radio again. It's a different synchrotron radiation process. So here is another example. Andromeda galaxy. This is optical picture. This is infrared picture in 12 micron. So the dust and polycyclic aromatic hydrocarbon, that kind of very frozen stuff is only seen. Here in X-ray. X-ray, whatever is seen, that objects are mostly medium degree hot. So there is not atom molecule. They are plasma, thermal plasma. So X-ray hot, million degree hot, 200 degree Kelvin, 6000 degree centigrade. So different temperature things are seen in different band. So star, warm, visible, cold, frozen, infrared, very hot plasma, million degree hot in X-ray, and non-thermal plasma is seen in radio. How this radio plasma hits the galaxy, what it does to the cold gas, warm gas, hot gas there. If we understand that, we can understand basically how black hole and the galaxy interplay. That is what is the purpose of AGN feedback. Let me tell you one more quick thing. This is optical picture of a galaxy, spiral galaxy, very nice spiral galaxy. Here is the neutral atomic hydrogen gas. Neutral atomic hydrogen. How do you see? We see because the hydrogen atom, which has a proton and an electron, they are all ground, both are ground state. Fundamentally, you can say that when the spins are parallel, they are of slightly higher energy. When the spins are antiparallel, slightly lower energy, more stable. In this case, the energy difference between them, delta H nu, that is so low in energy that the wavelength lambda frequency comes in 1400 megahertz radio, not optical. Optical gets alpha. So looking at that kind of small transition of GMRT radio telescope, you can see the cold neutral atomic hydrogen surrounding the stars of the galaxy. 6000 degree atomic neutral, that is not even ionized, not even molecular. When you look at how this galaxy's gas is approaching or receding through Doppler effect, then you can see this kind of thing. So this is the gas, atomic hydrogen gas of the galaxy. But one side of the galaxy's gas is slightly red shifted, other side of the galaxy's gas is slightly blue shifted. That is because the gas is rotating around the center. When something is rotating around C, this way my hand is coming towards C. This way my hand is going away from me. So that is how we determine at what velocity and what radial distance the gas is rotating around the center. It's very simple, classical. This way one can determine the velocity field of galaxy's rotation. That from the center of the galaxy, distance outward, at what velocity the gas is seen to rotate. 150 km per second, 100 km, 150, 200. When you go from center to outward, the velocity increases, and after a while it remains same. This is a flat rotation curve. This is how this will inform that the spiral galaxies, infrared galaxies, all of them are buried inside a dark matter halo, whose gravity only is felt by the rotation that we can observe, but it doesn't radiate anything. Okay, so that way, understanding galaxies in multiple wavelengths and multiple components, how they play with each other, that is what is actually exciting, and that is what is my research topic. We will go to that topic. But this is one last slide I will be explaining. Suppose there are two spiral galaxies. When they come under gravity, they will be going around each other. They will be trying to watch. When they watch, like I described, the satellite falls on Earth. Because friction of the atmosphere, it will slow down, you lose its angular momentum, it will be dragged inward. Similarly, during this merger process, this kind of tidal tail forms and gas fall toward the center. So a lot of star formation happens. It feeds the black hole. It creates a lot of wind. In that process, the cold gas from these two galaxies are merging together gets blown away. When it is blown away, by the time the merging of the two galaxies finishes and become one galaxy, they will just get clock. They will lose their sense of rotation like a disk, they will become elliptical like galaxy, but they are devoid of cold gas. This is one of the theory called AGN feedback. So during the merger process, the cold gas gets expelled out of the galaxy, and finally the remnant does not retain any kind of cold gas to form new star. So in this process, jet also draws the same one. That's what where the topic is. That how the jet affects the galaxy, we want to understand. Without that, it is not possible to understand the two classes of galaxies, spiral and elliptical. Why this people has more gas and star formation continues, but this elliptical has no continuous star formation. For billions of years, they are not forming new stars. So I will end with this topic, and our citizen science discovery basically is contributing to the understanding of this AGN, active galactic nuclear black holes feedback onto the galaxy, how the black holes grow and star formation growth of galaxies go hand in hand, how they affect each other. This is a big question, like fundamental question like difference between plants and animals. The big difference between spiral galaxy and elliptical galaxy, basic two type of galaxy. Why we see such a remarkable difference in galaxies? How it has been happening since last 13 billion years? It's an important problem. So discoveries with this kind of citizen science and how black holes plasma outflow happens and affect the star formation is an important topic. Thank you very much. Any question? You can ask now or later or anything is great. I will not be hearing now.
So, one of your discovery of spectra in 2011, you said it's quite non-trivial to see a collimation jet from a spiral galaxy. So why is it so common for elliptical galaxies? Do we know the mechanism why elliptical galaxies?
That is very standard question, but good that it comes in the thinking process. The reason is that this kind of jet comes out from elliptical galaxies. Elliptical galaxies are massive and big. So big galaxies are actually hosting bigger or more massive black holes at the center. So to launch this kind of plasma jets, the theory is that you need to be having a massive and spinning black holes. So in the process of this merger, you end up creating more massive M1, M2, and again accretion of gas. So by the time the merging process finishes, the mass of the black hole has grown. Mass of the galaxy has also grown. So to have a central engine, like a bullet engine, powerful engine, all this process has to happen. That is how automatically the bigger galaxies, spiral elliptical galaxies have bigger black hole launch jets. Why the rare thing happened? Slowly after our discovery, Indian astronomers and many others started discovering more. And they have now automated the process to discover more. What they have found, millions of them have been found out very recently, by citizen scientists have again. What they are finding is this kind of spiral galaxies have been left alone. They are not merging with anybody. They are kind of isolated people. So they are probably the first massive spiral galaxies that form in our universe who are left with no neighbor kind of thing. They are not merging, they are not interacting, but slowly, very slowly, like slow cooking, slowly they are growing over billions of years. This elliptical galaxy through merger is a fast growth process. That is probably a very slow passive evolution process. There is slowly new development. Yes.
So apart from the fact that elliptical galaxies are on the average more massive than the others, is it also what is questioned? Does it also have to do with the moment of inertia being more for an elliptical galaxy in its rotation as compared to others?
Moment of inertia more is a slightly different concept. What I mean to say is that in spiral galaxies, all the stars and gas rotating in the same plane. So that means they are all aligned like solar system thing. That is flat disk, like perfectly like a dosa, very thin. But elliptical galaxies, stars are rotating faster, obviously, but they are rotating in every possible plane. Like some gas star will be moving this way, the same galaxy, another star will be moving this way, another will be moving this way. So there is no preferred plane of rotation. So the mass is more, velocity is more, but they are not aligned. So in the process of this merger, basically, L1, L2, which are parallel, by the time you end up, every star has a different L, uniformly distributed almost in the 3-4 part.
If each of the stars is going their own way,
Different.
then the collective moment of inertia will end up being very small compared to.
That's what that is uniformly distributed ball kind of thing.
Yeah. Compared to then a spiral galaxy.
It is determined by this is represented by simply mass. There is no L.
So you say spiral galaxy is everything is in one plane.
Uniform.
Elliptical galaxy
Are random.
it's random. So the collective moment of inertia will end up being smaller in an elliptical galaxy,
Yes.
although it is more massive.
That's a bit funny way, but this is how the life is. But the first galaxies that forms in our universe is of this kind of thing. Slowly, the gas goes around the center and the spiral galaxy grows. By the time you become a proper galaxy, they merge with another one and starts growing to become an elliptical galaxy.
The current discovery of this emitting this monster black hole,
Yeah.
the galaxy is spiral,
No, both of them are actually elliptical.
both are elliptical.
So there is nothing stops elliptical to merge, right? Everything just gravity. Some other time, probably the other bigger galaxy was also an alien, was also ejecting jet. We don't know. Because the jets survive for few 10 millions of years. The galaxy themselves are 10 billion years. So jet process is a very transient phenomenon in the life of a galaxy.
Are there any estimates of the density of the plasma or the velocity?
The energy of the plasma is estimated. For example, how much is the magnetic field energy? How much is the particle energy? The energy of the whole block. Because you know the luminosity. From you can consider this plasma like a radiation, and you can estimate like what is the pressure there. But that way, otherwise, there are indirect way of finding out what is the energy. For example, when it heats in a cluster medium, surrounding medium is thermal plasma. This is non-thermal plasma bubble. When the bubble goes and expands, it will push aside the thermal plasma. Thermal plasma is directly observed by X-ray. So you can determine how much is the size of the cavity. Temperature of the outside medium you know the cavity is volume. So PdV, if you work down, if you figure out, that is the energy that the plasma must be having to push aside. Then now indirectly many things are figured.
On the related note, this famous story that G.I. Taylor was able to find out the estimate of when the nuclear bomb happened, and then they published a photo of mushroom cloud, and from that he estimated the
Energy.
wavelength of it. So you have sort of a fountain which is a mushroom cloud. So is there any? Can you do a self-similar or something like that? And
We'll try. We will try that. The next observation is actually to see if at all any gaseous medium you can see which is being kicked by the plasma. Then we have direct velocity of the surrounding mediums, how much momentum it is imparted. So directly from this also some indirect estimation is possible. Because it's such a weird system, we cannot assume many standard things. Even properly the shape is not really known. How it is trapped there, we don't really understand. The standard thing did not apply, it was just a discovery. Many other things can be. And a simple question. For example, why a galaxy rotates, what is made of, what is it made of? Anything is fine.
Why is there bipolar emission of black?
Yeah. How jet is actually launched is a very complex thing, nobody really understand. But one simple thing one can describe that, for example, if you something called magnetic flux freezing, you can ask you. Suppose you have this kind of a like pot or spew, you have a gas disk which is rotating. assume that the gas, the magnetic fields are this way, like passing through. And simple bar magnet, you understand that magnetic field strength will be proportional to the number of field lines passing through unit anyway, right? So if you rotate it, the plasma and the magnetic field are kind of frozen to each other or stuck to each other. Like you make a very plate of your hair, they get, by the time they are coming closer and closer, the magnetic field getting compressed and compressed. The field increases. So here this very close to the black hole, the B field increases so much that the QBV, whatever you will be calculating, that force is much stronger. The particles are just following the magnetic field on this side and escape. They have so much of volumetric, so sharp beam they have created, it can go 100 times farther than the galaxy depths. I did not show that megaparsec size, in million thousand light years. If suppose the galaxy is actually at 20-30 kiloparsec size, it can go to million parsecs. That is how it remains collimated to that far. We don't really understand. Certainly, it is not going inside this partial radius. It is all happening outside. But before it goes inside, it is lost. And it is going to affect outside, magnetize the whole universe, kind of thing people speculate. That this is the process that the galaxy shoots out the magnetic field, basically magnetized plasma to far away. It can reach another galaxy. So very wide things are there, but this is what excites us to study more. Any other question?
Yeah. Any of the astronomical data that telescope records, like it has to travel through the space, enter the atmosphere, then only it can have whatever the readings that you have.
Yes.
But does the atmosphere it has any background noise which affects the data, and how can you take care of the precision of the?
Yeah, there are many ways many people do depending on what wavelength you observe. For example, you cannot observe stars in the daytime because the sunlight, which is optical light, is scattered by the atmosphere, and that is brighter than the star themselves. Okay, very similar thing. You cannot observe the background star in infrared because our Earth itself is a block which is radiating at 37 degrees our body temperature, right? So you have to go to space, so that the background or the star to star in between region, what is the temperature? Sub-zero, because there is nothing to radiate, nothing to heat there. So that is how different wavelength people have different way of handling. One go to space, another, for example, radio telescopes are big. But the atmosphere, whatever light is coming, like twinkling of stars, the atmosphere also makes kind of twinkling to radio. So you observe very fast, or observe indirectly what is the twinkling happening, and compensate. Something called adaptive optics in radio, in optical astronomy. You shoot out the laser beam, and you observe the laser beam, how the laser spot fluctuates, and same correction you make the star or planet observation. Kind of compensate backward and add them on. There are many ways of doing it, and this is what we have to do. People are thinking of putting telescopes in moon to the low atmosphere.
But is adaptive optics implemented?
Yes, yes.
Talked about.
Yes,
Implemented.
everywhere. You cannot escape from there. You have to publish it in international paper.
No, but then there are composite pairs, is it? Are you?
A small part actually is compensated. Suppose the big mirror, because of gravity, is bending. So you take an actuator. India is making that kind of actuator for 30-meter telescope. You deform the mirror in the opposite sense, because it gets compensated. The other thing will be that you observe something spot there, how and compensate the observation. I'm not going to do it today. In the radio astronomy, same thing happens. You look at a fixed structure star, and then you go to the source. Then look at the fixed structure, the point source. Go to the source again. So whatever the atmosphere is doing, for the fixed thing that you know, you compensate for the unknown structure. The galaxy I will look at the unknown structure, but some telemeter I will look at known structure. But the atmosphere doesn't change that fast. So I will compensate what changes the atmosphere is doing. Anything else?
questions. Let's thank Anand again.
Thank you.
Let's meet in the coffee. Okay, coffee. Thank you, Anand.
Okay, thank you very much. Thank you, everyone.